This conference will now be recorded.
Can you speak a few lines, please? Please. Your voice is not coming. Okay, Mr. Krishnan. Okay. Thank you so much. Thank you.
This conference will now be recorded.
So now we are going to start the second session of this FDP. So welcome everyone to this second session of this FDP. It is my pleasure to introduce our esteemed resource person for the second session, Professor Ravi Sharma sir of IIT Roorkee, who is going to talk to us on the very important topic of petroleum geology geophysics. Professor Ravi Sharma sir is currently working as an assistant professor in the Department of Art Science, IIT Roorkee. He obtained his PhD and MS degree from Colorado School of Mines, Colorado. He has more than 16 years of professional experience in petrophysics, rock physics, and Q1 geophysics, and more than 5 years of experience in research and academia. He has successfully handled multiple high-value projects for helping the management with economic feasibility and timely decision-making. He also has extensive experience of working in multiple oil and gas basins across the world for characterization of formation and fluids. At IIT Roorkee, he is teaching some of the best industry-oriented courses in formation evaluation, seismic rock property characterization, and petroleum engineering. He is also involved in setting up a unique and top-of-the-class laboratory for supporting experimental and modeling investigation in petrophysics and rock physics. He has also been on the review board of most Q1 and Q2 journals in geoscience and petroleum engineering, and also on the electoral board of Journal of Applied Geophysics and Frontiers in Earth Science. He has more than 30 international and national publications and presentations to his credit, and organized multiple advanced courses for training the existing and upcoming manpower. Please join me in welcoming Professor Ravi Sharma sir. Over to you, sir.
Thank you, Dr. Puken, and thank you for this introduction. And welcome all the participants. Today we have some limited time on hand, but the topic is really vast. So I would like to touch upon some of the basics and would like to take you through some special investigations that I do in my research, and which encompasses most of the spheres of geology and geophysics. And that's the beauty about this integrational work here. So let me start with the So this is the first big picture as I would like to introduce. Sorry. This is the first big picture. Yeah. Sorry for the lag. I think it's for the bandwidth. So as you see, there's some seismic sections showing on the very left. And then you can see, of course, there is some geology over here. You can see some gentle dips and anticlines. Then you can see some stratigraphy, how they're continuous and not. And then we have a porosity models. So what is happening here? What is the big picture is about? So this picture is integrating your very routine and classical exploration methods like seismic, which is still like one of the essentials of doing exploration near to the basin. Then it has some wells here. You can see these wells, these wells over there. Yeah, as you can see here, right? So these wells, along with the seismic in the inverted section, when we inverted the seismic data using the wells, it gives us some porosity values. So this porosity values used in the reservoir simulation model for the initial porosity guesses. And right later on, we adjusted with the more discrete information, more detailed information available at point data. And we simulate that. And we simulate that to create a second saturation scenario. Using that saturation scenario, we create saturation logs and fluid substitution log and try to predict the petrophysical properties in terms of velocity, in terms of moduli, and then compare the two impedance. And we see the difference where the fluid has moved and where the fluid is left out. So essentially, the best use of that geology geophysics combinedly is being made for making out how the fluid can be taken out, which we know there in the subsurface, and whichever is left out, what technologies can be used to take that left out fluid. So I designed my talk with the following outline. To start with some basic concepts and definition, I'm told that it's a mix of class. So there are some engineers also who might have not looked at the basic definitions in terms of geology geophysics, and then some general introduction in terms of subsurface pressure, subsurface temperature, subsurface shows of the hydrocarbons, general geophysical exploration, including the top of the class is well logging and seismic prospecting. So I have included the two. There are other and not less important also. There are other, but we are not taking up for the case for this particular class because we have some limited time. And then I had some special investigations to show you how fluid substitution is important to understand, how seismic rock property characterization can help you understand your subsurface formations, how digital rock physics can help you simulate a number of scenarios, and possibly, if we have time, we'll touch upon induced polarization. So the second is, so start with basic concepts. So I think you have seen this image quite often, and the only idea to bring it here is that we all know that we have almost tapped into most of the high quality oil in terms of its access, in terms of producing it. And we have also touched a number of reservoirs with medium quality reservoir rocks. Now the investment of energy in terms of resources and all, they're going towards shale gas and the low quality oil available in tight gas sandstones or the coal bed methane or the hydrates. Of course, there are large volumes available for these, but they're difficult to flow. We all know, right? So this is tricky. So as we want to produce from these resources, we need continuous drilling and more drilling, and with better technology. So the constraint is, how does that technology, how do you decide what technology do you need, and whether you have better characterization of the reservoir, whether you understand the reservoirs, what technology would be used in your reservoir. So just to begin with, very basic definition: what is petroleum, what is total petroleum system, what is world oil reserves in production, and OPEC peak oil concepts. So to begin with, we all know OPEC is a very important organization, and founded in 1916 in Baghdad. Founding members were this. It still controls almost 80% of the world's proven oil reserves. And from a latest publication in OPEC Annual Statistics Bulletin 2018, we have this status with us, in which we are showing that Venezuela is still sitting at the top. But because this is not a very, the model of the class is not interactive, but otherwise I would have liked to know from you, why do you think Venezuela is still sitting at the top, is not able to make full use of its resources? And some of you might be knowing it very well, that it's mostly heavy oil over there, which is not making good economics in these days. So as you see here, OPEC 81.89% and non-OPEC 18.11% of the total proven oil reserves. In terms of net addition reserves, how OPEC and non-OPEC countries are doing. So if you see in terms of billion barrels net addition to reserves, it is around to the tune of 262.5 of the OPEC countries, and non-OPEC countries are not doing very good on this scale. So that being a bit of concern, not too much, but we still have lots of huge amounts of reservoirs available with us. In terms of investment, $1 billion per year, as per the same study, and if you look up to 21, we still have at least 10 projects coming up, worth like $15 billion per year of investment. So it's not like the conventional scenario, the oil and gas scenario, is going to die down. I don't think so. I mean, and I have reason to believe so. Companies are still investing a lot of money into these resources. So So there was a concept of peak oil, and why I believe that it's not going to go away anytime soon. Not only that, the renewable energies and the alternative energies, they need to come up at the commercial platform, and to be used by the public at large. They don't have very successful models so far for most of the renewables. For the oil and gas, the concept came around 1965 to 70. It says peak oil, and given by King Hubbard, which says that there is a hypothetical point in time when the global production of oil reaches its maximum rate, after which production will gradually decline. Now, that was perhaps given with a lot of inputs available at that time, and the most important one of them was the discovery to extraction cycle was very long. 30 to 35 years. Now, if you look at this times, the time that we are living in, and you would like since we started producing oil in late 18s, we have already consumed the first trillion stock tank barrel of oil. It was consumed up in the first 50 years, and the second trillion is already booked, and it is recoverable by the current technologies, and it would be consumed in the next 30 years at the rate of 36 billion stock tank barrel per year. Now, the third trillion barrel will be produced from the EOR operations worldwide. So this holds the key here. This holds the key. This word holds the key here. That if you have to, make sure that you get this third billion stock tank barrel, you have to be very smart with your EOR techniques. What kind of techniques you want to use? So in terms of overview of the world oil, we have extra heavy oil 25%, conventional oil 30%, heavy oil 15%, and the oil and sand bitumens some 30%. And just to give you a brief idea, as we have gathered information from the oil and gas journals, of the total 11 to 12 trillion OIP with 22% recovery rate, it comes around like 3 trillion barrel. But just take into account that these 3 trillion barrels does not account for all the kerosene oil that is still there. So we are not still counting on the kerosene type of oil. The estimate did not count the kerosene type of oil. Some pictures for the one who doesn't have a very good view about what do we call very light crude oil, and the light crude oil, and the heavy crude, and the heavy sour crude. And some of the conventional crudes world over, how they look like the blended crude. So I have put some of the crudes as they look as they're produced from the field. So this is 10 API Venezuela oil versus Barrow Island 38 API oil, and Nigerian light 37 API. So I don't know, any idea about what? So maybe in the interactions at the end of the presentation, I will ask from some of you what is the API for the Mumbai high oil that we produce in India. Mumbai high oil. What is the API for Mumbai high oil? Whether it is sweet or not. So that's a tutorial. So phase diagrams. We know that a lot of production facilities are based on what kind of fluid are we going to produce from the reservoirs. So definitely phase diagram plays an important role in order to understand at what pressure and temperature what product will be out, and what facility do you need at the surface to store that. So an essential part of the exploration program here. And what make economics? The hydrocarbon pore volume, which is nothing but porosity into 1 minus saturation, as we do in petrophysics. And if you want to do OIP, you just take a summation of these into height and the area in acre feet. The same thing in OIP, which is with unit stock tank barrels. The field equation is given as 775 into area into height and all those things, and recovery factor with formation volume factor of oil. This is an interesting variable, and we need to understand what for recovery factor. We already know that 22% worldwide average recovery. For some of the good reservoirs, we have even recorded 36%. For gas reservoirs, we have even recorded 80%. So it varies, but on an average for the oil, we consider 22% with 11 to 12 trillion barrels of oil OIP. Now, formation volume factor of oil is nothing but defined as the volume of pound mole of liquid at reservoir conditions to the stock tank conditions. And this is a change in the volume fraction when you bring the oil from the reservoir to the stock tank barrels. So this is the formation volume factor of oil. If you put that into this equation, you get the OIP. So having looked at some of the basics, we also have a basic of the international crude benchmarking. So there are some of the very famous indices, Western Texas Index, Brent crude, and Dubai. And these are the geographical locations where they're all applicable. So you can see Brent is almost used around the world. Dubai is more famous in local around the Indian Ocean. Is more preferred in while trading within the US or somewhere, some places around. And just for on the just for curiosity, I put that this is a very large crude carrier, and this is no less than the CS Tower in Chicago. This is almost to the height of the length of the crude carrier is almost CS Tower. So a huge amount of logistics and economy is involved in carrying out this oil and gas business on daily basis. So a very sensitive business and a very holds a high potential side for any economy of any country. So how does this crude occurs in the subsurface? So we know that it occurs in subsurface, right? So but how does it occurs? So it has four main components. It occurs in continuous phase, it also occurs in isolated droplets, it occurs in dissolved states, and it's also associated with kerogen like source bed, which is nothing but like kerogen beds, right? So main four modes: continuous mode, isolated droplets, dissolved hydrocarbons, or source beds. So when we say the only mode of significance is continuous mode, because that is the only place where we are hopeful of getting something out of this. And this is the only mode with any form of relative permeability. Residual oils indicate hydrocarbons have migrated through the oil stains rock. Dissolved hydrocarbon indicate that hydrocarbons are present in molecular form, but do not demonstrate that bulk oil is present. Yeah. And the hydrocarbon with the source rock is generally the hydrocarbon with kerogen, indicates that liquid oil is available to the system, may be productive with horizontal drilling or fracture stimulation or some temperature treatments in places. So very important to know that these mode of occurrences and what kind of oil they may carry and whether they're productive or not. So we say continuous phase is called show type 1, residual phase is called show type 2, dissolved phase is show type 3, and show type 4. And the bottom three are mostly in the non-productive zone. To produce them, we need to put extra money or extra energy into the subsurface. A continuous phase could be productive if you have really a good continuous accumulation of this oil. So in the exploration stage, this will be looked at the trapped oil. This will be called as a migration, and this will be like hydrocarbons are there in the system, but they're in the dissolved small droplets forms, and then source rock. So just remember, continuous phase is the one phase mode of occurrence which would be mostly productive in nature. The rest three will need additional investment of energy. Okay, so just defining a bit more into the what kind of origin do you expect for the four modes here. So as it says, continuous phase, a slug of filamented oil with a continuous connection through pore networks. So this continuity is very important here. Otherwise, we have a lot of wettability issues to make it continuous. Migration, some of the forces that helps. So what is migration? It helps oils to reach reservoirs away from the source beds, and the force that is mostly responsible is the buoyancy force, right, which has to act against the gravity also. So it is calculated at the height above free water level and the difference of water density and the hydrocarbon density. So this is one of the main forces responsible for making the oil reach its reservoir. The other forces, even after buoyancy forces, then you have these capillaries to be taken care of, where you have this entry pressure, and this is saturation 0 to 1. So when you're 100% saturated and oil is trying to migrate into the reservoir, you have to encounter entry pressure. You have to overcome the entry pressure. Entry pressure is the pressure of the capillaries, where you can do sigma cos theta on R, and which is inversely proportional to the radius of the capillaries. So larger the capillaries, easy to get into the reservoir. Smaller the capillaries, it is hard to get into the reservoir, right? So buoyancy is going to decide like how much of the entry pressure it has to overcome to get into the reservoir. And this is some of the pictures. These are some of the pictures that you can see. So reservoir in continuous form looks like where network pores are all full with oil, and these are the continuous filaments. It could be in a streak of oil, but it has to be continuous. Only then there is a chance of making it. And in the waste zone, they all look like isolated. They all look like isolated, small filaments, but mostly like isolated. It will be very hard to take them out. So a bit more about the continuous phase. As we said, the minimum pore volume saturation of oil or gas which is required here is 10% minimum. The continuous phase range from 10 to 90%. 10 to 90%. The ability of reservoir to flow oil will depend on the percentage of pore space saturated with oil versus water, and the continuous phase occurrence may or may not have commercial productivity. It is still a doubt. Even though it is continuous, it may still have reasons to not get produced. Subsurface pressure. So there are three essential components: show, pressure, and temperature. So if we can just run through them. So this is one of the main slide. In terms of pressure distribution, your subsurface is divided into three systems. So one is the shallow system, extending up to 10,000 feet or less. It is generally basin wide and exhibits normal pressure, and pore water free to migrate here. In the deeper system, it is not basin wide. It is more made into small, capsule, exhibit abnormal pressure, and generally consists of individual fluid compartment, as I drew here. Generally consists of individual fluid compartments which are sealed off from each other and the overlying system. So the shallow system, the deeper system, and some of the deeper basins even have the third compartment, which is again normalized pressure. So what would be the reason of these abnormally pressured? This is the second question that I may interact with you at the end of the presentation. What typically is the reason why do you have deeper system which is abnormally pressured, even though you have a third system which could be again normally pressured? So this is the typical cartoon that you see. This is the typical cartoon that you see, quite normal here, quite routine to be studied in your undergrads in petroleum. Lithostatic pressure and the hydrostatic pressure, and the difference is called overpressure, right? But the range of this hydrostatic pressure, if it changes slopes, then this hydrostatic pressure converts into overpressure here. And these are the reasons what I was saying about compartmentalization. So this is a schematic of how fluid moves in basins and they get accumulated. So up to less than 3 kilometers, you have this meteoric water storage, which kinds of get accumulated in these regions, and then you have compactional waters that percolates further down and gets pressurized here. And the petroleum fluids are also part of this this zone, and the thermobaric water, which gets excess pressurized and can vary from 2.5 to 3 kilometers. And what are the reasons for this basin fluid accumulation and the excess pressure in the systems? So I have listed a few, but the studies can go in further detail. So these are the mechanisms generating basin fluids, and that makes you feel overpressure in the subsystem. So you have clay mineral transformations, where the influx of fluid from compaction, evaporite, dehydration, and clay minerals transformations. And you can also have from dissolved buried evaporites, where a lot of fluid can be released. And then you also have maturation. So these are the three chief reasons where you have increased burial time with temperature, and then you have lots of fluid accumulation that causes high pressure zones in the subsurface. Yeah. So abnormally pressure systems, as we just went through a few slides, compartments have great longevity. They are not in communication with other regions outside. Top of the pressure compartments appear to be caused by carbonate mineralization, means alteration as their diagenesis. Generation of oil and gas within the compartment plus thermal expansion, pore fluids eventually causes fracturing at the top compartment seal during periods of basin sinking, and compartments releases pressure and pressure builds up again. So these are some of the sequences and periodic cycles that go on in causing these abnormal pressure systems. And in terms of pressure values, whereas under pressure or normal pressure is below 0.65, which is the pressure gradient for around 35,000 parts per million of saline, and then it can go from normal in the normal pressure range. It can go from 0.465 to 65, and can have a pressure in the reality can have pressure recording up to 0.9 psi per FIT. Pressure seals. Well, if I want to summarize, these pressure seals and the most effective seal. So this is the third interaction. I would like to know which are the common seals, and which are the most effective seals. For the carbonates, for this for having a very good seal of the petroleum system. So of course there are some reasons listed here, in which one of the reasons is mineralized zones associated with the top of the seal generally are found immediately above the seal, throughout the seal. A few recognized penetrations of the lateral seal by a well are clearly seen as with faults. Abundant occurrence of seal in deep basin worldwide indicate the formation and maintenance of seals are parts of the normal basin development. So characteristic of fluid seals: impermeable across their thickness, completely enclose each fluid compartment, may be independent of local stratigraphy and structure, and may exhibit an internal structure of altering layers of permeable and impermeable rocks. So these are some of the basic characteristics of the seals. And finally, the last basic component, before we get into the exploration stage, last basic component of the petroleum geology is temperature. Of course, we all know that temperature increases from Earth's surface towards the center. Now, for the petroleum geologists, when we try to understand bottom hole temperatures, and especially the records are available from well logs, there is something called static bottom hole temperature. Static bottom hole temperature. So if anyone would like to comment on at the end, why do we need static bottom hole temperature in order to convert them into gradients, it would be really appreciated, because in many calculations, if you do not take care of the static bottom hole temperature, you may be looking at different salinity and different RW values. What are the RW values? This is the water resistivity values that we use in Archie's equation for calculating saturation in the formation. So if the temperature calculation goes wrong, then at a particular salinity, the RW goes wrong. So effects are cascading. So why do we need static bottom hole temperature? The methods are quite familiar how to calculate them. So gradient is nothing but heat flow upon thermal conductivity, and you have some of the quite well-known values, and the average value lies around 25 degree per centigrade per kilometer. And this is the typical calculation of bottom hole temperature, static bottom hole temperature, where you need some APG chart corrections in order to achieve your static bottom hole temperature. And this is some of the methods that are presented in Shelley. But I mentioned it because it is one of the important parameters to understand why you need this static bottom hole temperature. Okay, in terms of geothermal gradient, the common geothermal gradient varies from 1.3 to 3.3 per 100 feet, and the global average is 1.7 degree Fahrenheit per 100 feet. There are some geological reasons mentioned here. As it says, the lowest gradient found on the Paleozoic platforms are overlying Precambrian shields, tertiary deltas, coastal pull-apart basins, four-arc basins. Most Mesozoic basins give values close to mean, whether they are compressional or extensional. Salt domes have high gradients. Graben and half-graben basins have high gradients. And I presented that with some of the cartoons, that if you are facing erosional upliftment, then you can represent your temperature gradients using this model, where it says if this is a present day temperature level, present day surface level, and because of erosion or upliftment, the surface was here first, and then because of surface upliftment, you came here. So the stable gradient will have to re-equilibrize and will give you this kind of a path. So you really have significantly high. And then you have in the depositional models, you have, so you can see that this is the temperature, right? This is temperature and this is depth. So for the small depth, you're really covering large temperatures, so high thermal gradients. And again, if you have a lot of depositions and subsidence, then for this huge depth, you are covering a small temperature range, so low thermal gradients. And these are some of the cartoons for volcanic arc and pull-apart basins. And last but not the least is some of the famous lithologies. So when we put questions in some of the pan-India examinations about lithology and the thermal conductivity, a lot of students missed on these. But I'm sure, I mean, this must have been taken care of in your classes, where we are showing that there are a lot of lithologies in the subsurface, and they have quite a good number of overlapping thermal conductivities. But on an average, if you look at the median or the mode values, you have to start with gas, then oil, then coal, water, and then you have these shales here. And in terms of highest, you have salts, and then you also have quartzites. Some of the common rocks that we need. Coming to seismic prospecting. So this is the area which I found like people are more curious about what exactly, how exactly do we use this in terms of exploration. So this is there is a source, and then you have a lot of receivers around. You can have different type of sources. You can have dynamite, you can have vibrosys, you can have air guns, seismic air guns. Then the important aspects are geophone spacing, how far they are placed, short point spacing, short point offsets. These are some of the important parameters for seismic exploration. And then if you put that all into one picture, then you have this source here. You're sending energy in the subsurface at the interface of the difference in velocity and density, which is nothing but the impedance, what we call impedance, which is velocity into density. So you have changing velocity and density parameters here. So at every interface, the rays bend and divide into primary and secondary sources, and then using those primary and secondary energies, you can characterize your subsurface and look at the formation that are of interest to you. And those formations can be found out in terms of dimming amplitude, in terms of standing out amplitudes, such things, right? So some of the very common waves are body waves, which is of compressional and shear nature. Then surface wave, which are Love and Rayleigh waves. Compressional waves are the VP waves and calculated using K plus 4/3 mu upon rho. Some of the basic formulas where this is the bulk density, this is bulk modulus, and this is shear modulus. And similarly, shear wave, they propagate perpendicular to the propagation of the wave. The displacements are perpendicular, but the wave motion is in this direction, particle motion in this direction. And similarly, S waves, wave motion in this direction, and particle motion in this direction, and wave motion in this direction. Rayleigh waves are retrograde elliptical; they go back, but they keep moving forward. These are retrograde elliptical. And Love waves, again horizontal movement, and these are the waves which are mostly you experience during earthquakes, the horizontal waves. And if you carefully study the movement of the earth during an earthquake, you can tell the tentative direction of the source of the earthquake. So this is the wave package. You look for first primary in terms of P wave disturbance, primary disturbance. Compressional wave has a period, and then start the shear wave, and then the Stoneleigh waves. Stoneleigh waves nothing but the surface waves, the category of surface waves, right? And these are the definitions of the periods and the amplitude. So from crest to crest, you define a period, and the maximum amplitude is recorded from the mean. These are some of the velocity values that you record in terms of compressional waves, shear waves, Stoneleigh waves. And yes, this is the integration. Once you have these data, the geophysical data, the geology data, you need to put that into management system, integrated management system, to derive the value of information. So you can, value of information. This is a buzzword where you put all the integrated, where you put all the measurements together, all the surveys that you did, and you try to integrate or you try to reduce uncertainty by extracting the most value of each data. So in terms of data acquisition analysis, you have geology, geophysics, drilling, core logs, and fluid test in one compartment, and then you go to the dynamic part with some static model, and then dynamic model, and then volumetrics, production. So this goes hand in hand in terms of value of information. So the value of information is a concept, as I said, but first was introduced in 1961, and later on assumed a very change in definitions. But the last one in 2002 says it should be used primarily to manage asset management portfolios, and that's why it has lots of value. So I'm presenting you one case study here where you're looking at the time-lapse data. But of the 10 scenarios that are generated, I think you can see change in almost all the scenarios that are generated for the time-lapse scenario. And in terms of putting your oil, in terms of putting your well, so you have a location here, you have a location here, you have a location here. But in all the scenarios, the distribution of the pattern, the distribution of the color changes. The color changes. And so how do you reduce this uncertainty in terms of, even though you have data, but how do you reduce this uncertainty? How do you understand that which cloud or which pattern is the most trustable? So that's why you need a lot of value of information from other data sources. One of the information is the scale effect. So of course it is huge actually. The impact is huge in terms of scales. But I'm showing you one example here where it says there's a code, but if you change the length, the data running means if you measure it over 2 feet versus 4 feet versus a full interval, then the permeability values changes drastically. It changes from 373 to 705 to further values. So scale has a very important effect. So any constraint that you want to bring here, at what scale it is measured, at what scale it is obtained, it also has a lot of uncertainty to ascertain to. Okay, so some other important parameters in terms of reservoir characterization are anisotropy. So in the interaction, I would also like to know from you how do you manifest heterogeneity in the subsurface. So some people say anisotropy. Of course, anisotropy, but what tangible ways or what definite ways do you know in order to capture this anisotropy? So do you want to capture, have you tried to capture this in terms of the preferred flow directions, the lineaments, or have you tried to capture this in terms of the elastic components, or have you tried to capture this in terms of diffusion flow, like how the liquid would flow from a small capillary to a large capillary, again to a small capillary, how the flow would affect in terms of different fluid that can be there in the reservoir. So scale effects, anisotropy, some of the standing out issues in the reservoir, and to study those issues, we have in reservoir geophysics we have defined some domains. So first domain is the 3D surface seismic. See, I'm teaching most of the basics of these petroleum geology and geophysics before going to the special investigations. So some of the main domains here are 3D subsurface seismic. Within 3D subsurface seismic, you have attributes. Although we know they are very famous and everybody wants to use them, like instantaneous frequency, phase, amplitude. But then there are certain special attributes also that you can think of, maybe like curvature attributes, to look at the lineaments and the fractures. And there are some sweetness attributes that you can look at to look at the most probable density, high density distribution of oil and gas. Then you have time-lapse seismic. I showed you one example from here, quite reliable, one of the reliable methods, but then you have to bring in some constraints. Others are like geostatistics, and then special investigations to ultra-thin beds, because resolution is a big issue. You don't get high frequency component. So how do you deal with the tuning effects of the beds? And then the multi-component seismic, which is also getting a lot of traction these days to get 3-component data and try to understand separately from P wave and shear waves, or the difference of shear waves. Maybe a simple idea is fast shear and slow shear, fast shear and slow shear, and how would they fare slow shear, and how would they fare in terms of fracture reservoir? Can they be used directly to diagnose the fracture directions in the fracture reservoir if you have multi-component data? Similarly, from as we had see in exploration, as I told you in the very beginning, we are dealing with majority times we are dealing with seismic and well logging. So that's how we have divided our special studies within 3D surface seismic. So we had 5 components here: attributes, time-lapse seismic, you have geostatistics, ultra-thin beds, and multi-component seismology. And then in the borehole seismic, you have VSP, you have cross-well seismic imaging, and then you have passive seismic monitoring, which is also kind of very famous for all these hydraulic fracturing analysis, backflow analysis, passive seismic monitoring. And the third domain, which is we are not touching on this in this particular presentation, which is the electrical and the electromagnetic service. You must have heard of controlled source electromagnetic service, which is a quite popular method for looking at the resistivities of the movement of oil. Like how do they map resistivities once the oil has been displaced in the reservoir after production, and they look at the pockets of bypassed oil. It's a quite a good method for that, but it has its own constraint. So one of the very characteristic use of the seismic data. So on the left hand side, you see a picture here, and seismic data has been made to use as a direct hydrocarbon indicator, which got quite famous, and many companies wanted to use these direct hydrocarbon indicators, particularly in the pre-stacked domain data. Pre-stacked domain data means where you do not stack your signals obtained from different offsets. See, I told you there are some different offsets: source and then receivers. You have receivers, and then you get signals from. So you have some offsets. So some are called near offset, then near mid offset, then mid far offset, then far offsets. So in the conventional programs, all the offsets would use to stack and give you the value of these depth points. So at one depth point, there would be like 50 shots, which is called fold-edge data, 50-fold data. One depth is covered by 50 times or 90 times to enhance the signal to noise ratio. But in the pre-stack domain, they started looking at these stacks separately without stacking each other. Now that added value, a lot of value to the analysis, because it was realized that whereas far offset data got a lot of information about the Poisson's ratio, the near offset data has a lot of dependence on the angle of incidence, the energy that is directly transferred. So you have 3 classes. Conventionally, you had when you started using these seismic data, you had 3 classes: class 1, class 2, class 3, and this is the line of zero reflection coefficient. So some are positive and some are negative reflection coefficient. Reflection coefficients are nothing but it's a simple mathematics, and we just looked at in the previous slide. So this is the impedance. So second layer impedance minus, first layer impedance, and the second layer impedance minus first layer impedance. This is a reflection coefficient. So these are nothing but reflection coefficients here. So class 1 says you have a positive reflection coefficient, but the reflection coefficient changes as you change the angle of measurement, as the angle of stack. So these are the different angle stacks here, So with angle stacks, the value of the reflection coefficient changes. It comes down and then becomes reverse. The polarity reverses, becomes negative here. And the class 2 goes from very low positive to very low negative, but in both the cases, the values goes down at larger offsets. Larger offset means larger angle stacks. And the third case, it starts negative and keeps growing as negative. So class 3, there were 3 classes conventionally defined. So this is one of the practical use of the seismic data in the industry. And a lot of reservoirs have been identified based on direct hydrocarbon indicators. And people have also used in areas where there was not much data around. So in kind of wild guesses, to make wild guesses. Even up to this is true even for many of the American companies who were trying to find oil in Greenlands and barren areas around that. So in addition to these 3 classes, Castani and Swan in 1997 also came up with one of the one more class. It says low impedance as well, but reflectivity decreases offset. Low impedance, but reflectivity decreases with offset. So this is nothing This is a reverse of the class 3. You had class 3 here, and then this is reverse of the class 3 here, right? So it's class 4 sand. So quite useful in especially in the conventional reservoirs, sand reservoirs. Now coming to after seismic, we have well logging. So this is one of the method that this is primarily responsible for success of the exploration targets. So you can see this drilling rig here, and this is the design of the subsurface well, and you can see the casings are put like in a Christmas tree pattern. Okay, so these are the close. This is a close view of this drilling. So this is what is important for us as a well logging or a petrophysical or formational evaluation engineer is to understand how much of invasion and where the invasion has occurred. So because invasion changes the response of the tools. Any tool that you measure in the subsurface, it has a response, and the response will change if you have your drilling mud going into the formation. And invasion happens the moment the new formation is drilled and the mud water is exposed to the formation water. Now, depending on the whether it is drilling with high pressure, lot of pressure, or low pressure, or even pressure, the fluid may come out of the reservoir. This fluid may go in the reservoir, or no exchange may happen. Very little of exchange happens. So. This is one of the basic properties, or one of the basic areas where you should look at whether the invasion has happened, because all the logs, almost all the logs except LWD. So why LWD? LWD means logging while drilling. If you put some of the log suits around this drill bit, let's say this is the drill bit, and you put some log suits here. So the moment it is drilling, it is also measuring the formation. If you have LWD arrangement in the drilling rig, you have chance that you will not be measuring the effects of invasion. But if you leave the mud for a long time before your logging rig arrives, a lot of fluid usually get into the permeable formations, the porous formations, basically the formations of interest to us. So drilling fluid systems, some of the holes can be drill compressed here, but this is not of much use to us except in the uphole surveys. Then you have water-based mud, then you have non-aqueous muds. Within the water-based mud, you have fresh water, salt water. Within the salt, you have NaCl, KCl. Similarly, in the non-aqueous mud, you have oil-based mud, you have synthetic muds, and there are a number of patented muds around available around. A lot of patents have been acquired on the different surfactant type muds or polymer type muds, right? And they have their different use. So like this freshwater mud and saltwater mud would be preferable where people do not allow you to drill for environmental concerns, concerns. Like in the California counties, they do not allow any company to drill with oil-based muds because they fear that the oil may seep into their water table and harm the community. Whereas that is also true that even though this is cheap, but then using water in the formation evaluation hampers a lot of information that you can obtain otherwise about the saturation percentage in the logs. So once this water goes inside the formation, it disturbs the saturation pattern, the water saturation pattern of the formation inside, and gives you a altered reading of the saturations. Okay, mud weight. So we just went through that mud has an important role to keep the oil well intact, not let the wall collapse. But then it has its own side effects also. So some of the side effects could be collapse pressure. You could be fracturing the formation. If you are above and below the port pressure, depending on the weight you have. So this is a design drilling program. This is what you wanted to, and this is your actual weight, how it is faring. Some of it is going above, so you need to bring it below. So these are some of the diagnostics that you need to understand in terms of having a safe well, drilling a safe well, and some of the repercussions of having over weight drilling is you have sometimes. So this is a safe window. Safe window means where the well will not be disturbed at all. Safe window. or you will have small breakout zones, and when you go above the safe window, you will start losing. So these are the results of the excess mud here. So what is happening here? So the excess mud has created some fine fractures in the direction of the sigma max, and sigma max, maximum horizontal stress. And these cracks can be clearly visible if you have very heavy mud in the well. It can create fractures. Versus when you do not have heavy mud, you have mud lighter than the pore pressure systems or the formation pressures, then you can get breakout, or you can get a kick also. So with the kick, the whole diameter gets disturbed, the whole sanctity gets disturbed. Then you may not have reliable measurements over there. So these are the ill effects and site limitations of the mud program, and you need to balance that very nicely. So we usually take that up in the well logging class also. And this is a very famous schematics from Asquith and Krygowski, which is a APG recommended memoir on the well logging, and it shows all the environment of the well logging system. You have a hole, then you have the diameters, you have mud cake, you have flush zones, you have invaded zones, you have uninvaded zones. Now, depending on the zones, you have lots of logs designed. Some log may only look in the flush zone, some may look very deep into the formation. So if you just look at the, let me go to the state. Yeah. So these are some of the logs and the limitations they have. So on the y-axis you have resolution, and on the x-axis you have depth of investigation. And you can see that some of the tools that have low resolution have very high depth of investigations. And broadly, the logging tools can be divided into three classes. One is the resistivity class, and one is acoustic class, and the other is relative class. Most of the logs group into three classes. So if there is some takeaway that you can have from the classes like this, you can broadly remember that most of the logs comes into either resistivity class, acoustic class, or relativity class. Okay, so let's see some of the important logs that we usually deal with. So these are all specialized logs. But some of the common logs are sonic log. Sonic log has a resolution of around 60 centimeter, but has a very low depth of investigation, around maybe 5 centimeter or 4 centimeters. Density, a good resolution, and around a reasonable amount of depth of investigations. Then you have gamma ray, neutron, but the highest is the resistivity logs, induction logs. They get up to 90 feet of investigation. So I wanted to mention that now you can imagine that if you have invasion, if this is a borehole, and you had mud here, and this is your formation, and this mud already encroached into the formation. This must have pushed the fluid of the formation away, so it will be profiled like this. This is the dispersion effect. So if the water is coming, it will try to accumulate here, and then this is mud, the mud filtrate, and then the formation water is there, oil is there. So this profile is already changed. Now, if you bring some log sonde here, and you measure this, some of these logs may not look beyond these flush zones or invaded zones. So they would be measuring effect of the invaded fluid and the formation fluid together. So this is the limitation in terms of allowing how much invasion you would like to. And because we are looking at invasion, it is important to mention that. And before invasion, let me go through this mud log. So as a practicing petrophysics, the formation evaluation engineer, I used to ask my manager that even if you cannot give me any good log, any advanced log, give me a mud log, because mud log can give you initial information that can be used as a ground value, because they are nicely prepared by the well site geologist about the type of rock they are looking at during the drilling program, type of fluid they are looking at during the drilling program. So it's a very important, very informative log, and serves as one of the calibrators at times if we have no depth issues. If there are no depth issues, mud log can serve as one of the calibration parameters. So this is the typical mud log. And remember, this is very important. You should always look for mud log in the system when you bring up your own interpretations using all the well logs. You must try to compare it with the mud log if available. So this is what it is saying. The lithology, it already mentioned, okay, this is mostly shale, then calcite, then some mixed lithology with sands and shale silts. So, and some fluid information in terms of C1, C2, C3, C4, C5, and the collective fluid. So you can clearly see this formation had some fluid effusions, this formation has some fluid, this formation did not have, this formation did not have, and the lithology is there. So once you have this, well log interpretation with you for using the all modern logs and the combination of logs, try to compare that with the mud log. So having spoken about the mud log, invasion is important. Invasion is very important in terms of modeling a number of reservoir properties. And this is, see, this is one of the very direct evidences of the properties. Seismic gives you all the indirect evidence, but well log is something which gives you the first most possible direct. If you don't have the code, at least you can believe the logs if they are nicely processed and acquired and processed. So showing you the invasion profile in 1D. So this is while drilling. So if you allow your well to sit and wait for the logging rig, let's say you have only budget for wireline logging, only wireline logging you can do. So you have to wait and for the wireline log truck to arrive and then do the acquisition. But in that time, this is the loss in the formation that is happening. So invasion is happening in the formation. 3.4 hours, 38 hours, 104 hours. So the fluid is keep going inside and it is changing the formation fluid profile. And what you will measure is the effect of this fluid combined with the formation fluid. And this is very dangerous. Looking at the 3D now. So let's say this was the wing that you were watching in the previous slide. So you can see that went inside. But in the 3D, if you see, so this is a sandbox experiment, and this is quite possible. So in the 3D, you see that these directions, they do not entertain the fluid to go much beyond some levels, right? So definitely there is an anisotropy of property. There is anisotropy of porosity and permeability in the directions, and it's important to know. So invasion, and that's why you when you try to understand the collective properties of the logs, putting together gamma, resistivity, density, neutron, sonic, you try to see the properties whether you see any anisotropy in the formation or not, right? Because then they will tell you that you also need to look at some other data set that can bring constraint for the anisotropy investigations. So this is the typical profile, as we said, flush zone, invaded zone, uninvaded zone, and this is the borehole. And if mud combination is like this, if resistive to the mud filtrate is quite larger than the rest of the water, and when we say water is the formation water, formation brine, okay? And formation water is always considered brine in default. Default, it is a brine. Brine will have less resistivities than the mud filtrate. So mud filtrate resistivities are greater than the formation water. So profile of the resistivity would be something like this. But if they are same, if they are equal, then the resistivity profile would be like this. So intentionally, it is taken care of that you have a mud which is different. Hello? Hello? Is everything okay?
Yes, sir, it's okay.
Okay.
Please continue.
So this is a step profile for the water bearing formation. Now, if you have an oil, what will happen with the oil? So just remember, the concept is rooted a little bit deep here. The moment you have an oil here in the formation, in your formation you have oil, you will have an annulus zone. Annulus zone means what? See, the annulus zone say it has a drop resistivity here. It has suddenly a drop in resistivity. And why so? Now, this is based on assumption. First assumption is the formation is water wet. So once the formation is water wet, it will like more water, and the water movement would be not easy. Now, once you have a push from the mud from this side, there would be a zone where the oil would be free to move, because formation is water wet, oil is more free to move, so the relative permeability of oil is higher. So once the oil leaves the formation, leaves this particular area, suddenly you have a zone developed where you have more water, most of the formation water. Okay, and this formation water is, again, as I said, we believe formation water is saline. So the moment formation, what is left in abundance here, it will have a drop in. It will have a drop in. Sorry, it will have a drop in resistivity. So this is called analysis zone. So this is the typical signature when you have oil bearing formation. When you have oil bearing formation with good amount of water also in the rock. We just went through this and we also understood, we just talked about this also. Okay, so as in seismic, we saw that there are some direct hydrocarbon indicated in terms of amplitude variation with offset, right? In tools, logging tools also, you know that there are certain tools that will help you determine something. So resistivity, all the dual lateral log or the induction logs will help you determine saturation. The natural gamma log will help you determine V shale. The electron density, the litholathy density tool will help you determine porosity. Neutron porosity tools can also help you determine porosity. And the NMR tools can help you determine the permeability. So having looked at these possibilities of the logs, we will just quickly go through the log section and we'll arrive at the spatial investigations. So gamma ray, the definition says any one API gamma unit is 1/200 of the difference in log reading between a low and a high radiative zone at the University of Houston. So all the logs are calibrated at the University of Houston pit with the known low activity concrete, Ottawa sand and Portland cement, and with the known concentration of radiative concretes, which is uranium 13 parts per million, thorium 4 parts per million, and potassium 4%. So once you have this combination mixed with this low activity Ottawa and Portland cement, you have a reading of 200 API units, and remaining logs are calibrated as per that. So similarly, there are other calibrations for neutron log, for density log. Okay, and once you have the gamma log, you know you have a gamma log here. So the typical range for clastic sediments like sandstones you plot between 0 to 100 or 150, and you have a curve like this. So more it is towards the higher values, more radiative it is, like it is shaly. And when it is low value, so people would jump into say, okay, this is reservoir, this is sand. So I would say no. The virtue of gamma is to tell you whether it is radiative or not. The virtue of gamma is not to tell you whether it is reservoir or not. So be very careful when you say gamma log is less than high. It means you have more radiative shales at some places and less of them at some places. Now the less radiativity shale is the reservoir or not, it is a matter of other parameters, other cross checks to be done. It will form a reservoir if it has good porosity. It will form a pay if it has good permeability and good saturation. So there are other cutoffs that it needs to qualify to be called as reservoir or a reservoir pay. Okay, so first you have shale and non-shaly zones. So a shale zone and a clean zone, we can also call them clean zone. So once you have a log, you mark the clean zone and you mark the shale zone, and based on these lines, these constant values, you calculate your volume of shale. Similarly, the SP log works on the natural current that flows in the formation. It does not inject any current. It relies on the natural current that flows because of the combinations of different ionic water movements, right, and the physical fluid movements. And they simply put a voltmeter, lower electrode down in the borehole, and it makes a natural circuit, and it measures the millivolt on the voltmeter. And again, any deflection in the voltmeter will suggest that the fluid has moved, because only when the fluid has moved, there will be deflection. Now there are certain criteria to understand what a deflection means. Deflection means, so here is the layout what deflection means. So there are few formations here: shale, thick clean sand; shale, thick shaly sand; shale, thick clean, thin clean sand; shale. So wherever you see thick clean sand, there are three parameters: it is thick, it is clean, and it is sand. Okay, so clean sand means there is no shale here, and thick means it has sufficient thickness so that the sonde can reside completely inside the formation. Sonde means the measuring sonde. can completely reside inside the formation. Whenever you have, so let's check one parameter, just one parameter. Whenever you cut short a parameter, let's say it is not thick, it is thin. So what happened to thin clean sand? Thin clean sand. The moment you came to thin clean sand, where the sonde was not really inside the formation, you have a drop in measurement. Not only you have a drop in measurement, you have a drop in shoulder estimations. So you have a drop in shoulder estimation. You did not get the exact thickness of the formation. So these are the effects. These are the after effects or the effects because of the thin sands, right? Similarly, if you have thick but shaly, again, if you have thick, so thick means the sonde was completely inside. It could be inside, and the shoulders were thick, still mapped. But even though shoulders were almost accurately mapped, it did not have the full potential of the sand. It did not measure the full potential value of the sand because it is dirty, right? So now from this you can also see that whenever the shale is coming, so if this is shale, this is shale, this is shale, this is shale, right? Whenever the shale is coming, the values are getting back to this line. So this line, the values are coming back to this line, right? That means there is a shale line. Shale line will always have, so I'm trying to say 0, but it will have a constant value. It will have some constant value. It will not have a 0 value because each shale is different in character. So each shale will have a shale line. Shale line means whenever the instrument will see a shale, it will get back to the shale. So this is the calibration point also. So whenever you see a shale, whether your SP is coming back or not, right? So whenever you identify, whenever you model your lithology, if you see you are modeling a shale, look at the SP, whether it is also showing whether it is coming back or not, right? So these are some of the effects of having thin sands or shaly sands or non-water bearing sands. Okay, so I'm telling you exactly the measurement that you should, the way you should look at. And when you have all the parameters satisfied, so there is a condition when all the parameters should be understood. Here is the condition, and this condition is tabbed here. So RMF and RW. So condition is RMF is always greater than RW. That I have already explained why. Because we believe RW is the formation water, and it is always saline. It is always saline. So when it is saline, its resistivity is less than mud filtrate. So when you have this combination, when you have RMF is greater than RW, the negative does not change. But whenever you have this reverse, what will happen? This sign will change. You will become plus. You will become a plus here, right? So remember this. The assumption changes, the sign changes. Okay, because this will go upside down, and the sign changes. The static cell potential value. The static cell potential value is the value which is obtained in a very thick, clean, wet sand. So there is another parameter: thick, clean, wet. So thick, clean, wet, no shale, only water, saline water, and is thick. So you have the best value, SSP. In all the other scenarios, you will not have SSP. You will have some other values. What we call other values, we mostly call it pseudo self potential. This is static self potential. This is pseudo self potential. Okay. So pseudo self potential is developed in which, like thick or dirty. Shelly means dirty. You have water, you have thick, but you have dirty, not clean. Okay. So these are some of the schematics or the cartoon that can be used to understand what kind of combination are we expecting in the subsurface and how to read that. These are some of the uses, correlation between wells, as I said, correlation for the bed thickness, like shoulder mapping, V shell calculation, and RW determination. This is one of the best use of SP logs, RW determination. So in the combination, you have this Archie's law, A into RW into phi raised to power m into RT, and raised to power 1 upon n. This is saturation exponent, this is cementation exponent, right? And this is phi, this is water resistivity, formation water resistivity, and this is true resistivity. So this true resistivity is already available to you from the deep logs, deep induction logs, right? Deep induction logs that look very deep, induction log. So you can identify a good zone. Let's say this is your sand, You can point a clean zone, you can measure it. So this is your gamma, let's say gamma ray. In the gamma, you found a sand and you mapped it into the resistivity, and you had a value here, right? You had a value, you noted this value, and you can use this value directly at RT. Okay, but RW, where do you find RW? We don't have a law for RW. How do you find? So in 90% cases, when you do not have information for RW, how do you get information RW? You use DST, drill stem test, or repeat formation tester. Okay. Once you have these tools run into the well, you can have some natural samples for the formation water, and you can have RW value measured. But if you do not have that, because these are expensive affairs, if you do not have that, what do? You do RW estimation using SP log. And there is a set method to do this calculation, RW calculation. And let's say you don't have SP log, what do? So in 90% of those cases, you start assuming, depending on the location on the globe where you are, whether in the polars, in the poles, or the tropics, or the equator, what kind of average salinity, sea salinity you have, and based on the average sea salinity, you assume your salinity to be like, whatever value you want. So typically we start between 35,000 part per million to 50,000 parts per million, depending on the location, if you have nothing given. And in my classes regularly, I make the people write a code in which we start with the fresh water, and the people and the students automatically have to determine the actual salinity value over there. Okay. Acoustic logs. So we did gamma and SP log, and then we have acoustic log. It's 6:4:11, so I think I will get some time. So acoustic log, it is more clear, it is more close to the seismic in nature that we just went through some time back, in which we had one compressional, one shear, and one stone lay waves. So compression, mostly acoustic logs look into. So conventionally we look into P wave velocities, right? P wave compression, P wave or compressional signatures. So these DT values, of course, we have shear logs also, but conventionally I'm saying we have mostly P wave logs, compressional wave logs. So these DT values are nothing but the delay time values. What is delay time? The time taken in coming from this first receiver offset to the second receiver offset. So this is the source transmitter. You have first receiver, you have second receiver. So this is near receiver, far receiver. So the math is easy. You have a wave coming from here to here and to here, and the same wave is going here. Now if you subtract this and this and this part, what will happen? So in the first path, if you subtract the total, from the total path, if you subtract this one, what will you get? You get only this path from here to here. So this is basically what? This is formation. This is formation. It has nothing from the mud. It has nothing from the sonde. It is only from the formation. So this is how we get delay time of formation. Now this itself has a lot of uncertainties. When the hole gets bad, when the mud gets heavy, all the uncertainties. But once you have this kind of log, so this is the DT value, delay time value, and this is the DT value of the matrix. This is the DT value of the fluid, and again matrix. This is a similar formula as you had in shale for the gamma ray. You calculate phi. So phi from sonic. Okay, so this is a way to get phi from sonic. And similarly, you have a phi from density. Again, you have a density log, you have a source, then you have near receiver, you have far receiver, you have a source, you have a near receiver, you have a far receiver. Okay, so depending on the attenuation of the gamma, this is the gamma ray source. Depending on the attenuation of the gamma ray, if it is less attenuated, it gets recorded here. If it is heavily attenuated, it gets recorded here. Okay, depending on the difference between the two, okay, you get this bulk density log. Well, there is another log acquired here. It's called lithodensity or PEF tool, but that's for the lesser attenuated gamma ray. Okay, and in the energy spectrum, this is electron volt of energy, and this is common minerals like from 0, 10, 20. So 0, 10, 20 means 10 means up to calcium. So if you look at the common earth minerals, for the common earth minerals, the Crompton effect is the dominant effect. And this Crompton effect gives you nothing but the bulk density value. And the lower energy level here gives you the PEF log, the lithodensity values. Okay, again, if you have this low bulk density values, you obtain the bulk density values. You have the true matrix value for the density. You have the true matrix value for the density. You have the true matrix value, so true value for the fluid. So you substitute these things, you get porosity from density. So see again, linear formula for porosity from density, linear formula for porosity from sonic, right? Similarly, linear formula for V shell from gamma ray, linear formula for V shell from SP. So it's kind of easy, but easy in well logging to calculate the parameters. But it has a lot of caveats to take care of. Once you are free of caveats, the readings are reliable. Similarly, you have neutron log. Like in density, you have gamma ray source, you have a neutron source here, fast moving neutrons. So they collide, right? Then you have a near detector and you have far detector. So once they collide, initially they lose some energy, and if they're captured in that form, they are called epithermal neutrons. If they further collide, and get captured, then they are thermal neutrons. And if they completely get captured by the formation, only gamma ray is released. So there are three kinds of logs from the neutron. Once you have neutron, epithermal, so source neutron and recorded neutron, epithermal. So you have neutron, thermal, and you have neutron, gamma. So there are three kinds of logs which have different, which are used for different characteristics of the formation. And resistivity log, we just went through this in the beginning, but just to complete the slides, this is what we understand that from mud, how the resistivities are varied from flush zone to invaded zone to true zone, right? So again, once you have everything, this is the formula for Archie's equation. And I'm telling you how the different parameters are obtained. So torsion factor typically taken as 1, A is equal to 1, it obtained from core. Then you have formation water resistivity, either you can have it from samples or from SP logs. Saturation exponent you can have from cores. Cementation exponent you can have cores and from image logs. Porosity you can have from sonic, density, neutron, NMR, resistivity, and then your formation resistivity you can have from induction logs and lateral logs and dielectric logs, all these logs. So this is 80 to 90% of the time you deal with Archie's law. Only in very special cases you go for dual water saturation, Waxman-Smith saturation or Juhasz saturation. Those are some advanced analysis for saturation, but typically from 80 to 90% you are good with Archie saturation, and it matches most of the calibration data also. And I'm showing you just one layout that I performed for a tight gas sand. So on the very left hand side you see the gamma ray caliper logs, right? And it's very bad, it's washed out, the caliper is very bad, it's very bad hole, right? So how do you work in such a hole, right? You have resistivity logs, so you can see a deep resistivity, the D-resh, and you have shallow resistivity, S-resh. They're almost overlying most of the time, but in places they are moving away, right? The deep resistivity is moving away from the shallow resistivity, but not too much. That means there's a lot of water. They're all looking at the same thing. Now, in this particular track, you have a density and then you have a neutron, right? So you're plotting density. Neutron is this blue color, and the density is this red color. And there is a famous saying here that neutron on the left and density on the right is the shell, right? Neutron on the left and density on the right. But remember, you have to be consistent with the units. So these plotting units have to be consistent, whether you're plotting in a sandstone or silicic system or you're plotting in a limestone system. So it has to be consistent. And these are calibration data, as I was referring to many times. These dots are nothing but the core data, the data obtained on the core, and this is how we are calibrating. So this is porosity calibration. Similarly, we have V clay calibration. We calculated V clay and we calibrated. You can see the match is like more or less reasonable for us. And we also have the permeability calibration. We did permeability calibration also for the zones which are highly permeable. We have data in the trend and at the space also with some values difference, of course, because we are not using the idealist models. And we have also good match for the irreducible saturation. Saturation which cannot move. So that gives a very good estimate of how much of water a formation can move actually. So this is a tight gas sand solution for Piceance Basin in USA. And these are some of the other applications that you can do with well loggings. I would go to special studies because I don't have much time left. There's 10 minutes left, but I would like to show this study to you, which is very close to the real scenarios. So let's say fluid substitution, and fluid substitution in carbonates is typically a more challenging one. So this is the mechanism how the ions are exchanged and the diagenesis sort of happens. So this is a rock and empty rock. What is happening here? So all the pores that had water before, this black color is all pores available for water, and these are all grains. So you can see that the grains are dissolved, became pore, and the initial pore space got filled with some cements. So the rock became empty rock, right? Okay, the space is almost changed, all exchange. So in understanding such rock, I mean, it is not easy. First of all, which phase of the reservoir you are encountering it, whether you would be able to understand the velocity in terms of matrix change. If there is a matrix alteration, if there is no matrix alteration, you can still believe the velocities to be infected by some fluid. But there is a matrix change also, it's really hard to understand. So this is the mechanism. It's going from deposition to early consolidation to marine cementation, right? So finally velocity is here. And similarly for the intercrystalline porosity, so this is moldy and this is intercrystalline. So pattern change in velocity is very different. And these kind of diagnostic plots are very important, extremely important. You know what is the range of a velocity in the reservoir, how it get influenced once you have cementation, once you have fluid, and only when you understand these forward models, you can interpret the data from the field in terms of change in sensitivity because of fluid replacement or because of change in matrix. Of course, change in matrix, trying to invert a change in matrix from the field data is extremely hard, very hard. And I'm showing you this practical example here, just because we have less time. So these are again a carbonate here, and there are two sets of carbonate samples here that I'm showing here. On the right hand side, same matrix. There's no difference here, same matrix, right? On the right hand side, we have this is almost fully water saturated sample. So whatever air bubbles were left, they were uniformly distributed. Whatever air bubbles were left, they were uniformly distributed. So this is like a sponge, you know, you have water everywhere and then you have some air, trapped air, but it is uniformly distributed. The moment you start production, let's say it went to 92%, from fully saturated to 92%. What is happening here? All the air bubbles got together. They like each other very much instead of being uniformly distributed. So they have a patch, they have patches here now, right? So we have some drain volume also, and we have already existing air bubbles. So instead of uniformly distribution, we have come to patches now. So how does your understanding of geology and geophysics helps you here? So you know, so you want to believe that the rock did not change, right? The porosity did not change. What changed? Only the saturation, and that to the pattern. Saturation changed by 8%, but the distribution pattern changed entirely from uniform to patchy. So you cannot imagine, or you cannot imagine the elastic property changes. Why do we need to understand elastic properties? Because that is something very diagnostic of telling you how the fluid is residing in the reservoir. Rock with oil, rock with water, rock with a mixture will have different elastic properties. And we create a lot of these forward models in the lab, a lot of these forward models. So let's go to field. So this is the typical field example. You have water at the bottom, you have gas at the top, and you have mixed zone. So, you know, in terms of energy, your mixed zone will be more critical to understand. Like it will not have a direct signature, right? You have water, you know the forward model. You have a gas, you know the forward model. But then to create a forward model for such a layer, you need to create that in the lab also in order to understand how much of the energy attenuation will happen in such a model, right? And there are some famous rock physics models, like, you know, this is the Gassman, and this is the differential effective medium models, right? And then some bound method. So when these are point method means if there is a point from the log, it can have a point from the model also. But then there are some bound method. Bound method means you have a distribution of property somewhere here, and I know from my bounds that it will lie between a calcite and a water. So these are bounds, a hard bound and a soft material. So if a composite is made of something very hard, something very soft, these are the limits of that. And the data plotting in the region will tell you how much of a combination of hard and soft it is made of. So essentially, what are we trying in reservoir characterization? We are trying to ascertain lithology. We are trying to ascertain fluid, and we are trying to ascertain how the combined effect of these can be understood, can be ascertained, can be diagnosed, so as to help the 4D programs, feasibility programs, new drilling programs. So this is the special study method that I was referring to. So right, so see, this is the data. Now you have a lot of data here. lot of data. So what is this data? It says clean sandstone plotting here at the top. Then you have consolidated sandstone plotting here. Then you have weakly cemented sandstone here. Then you have suspensions. Suspension is plotting where? Along the line of the fluid. This is the fluid line. And your suspended material is what? Plotting here. So this is where my geology and geophysics comes to the help. So what is suspension? So suspension is born out of critical porosity. Critical porosity. So what is critical porosity? A porosity that a particular formation during deposition can hold or represent, right? So let's say a typical porosity for a body centered cubic packing is 47.5. So let's say this is my critical porosity. Now above this porosity, so if this is the sample and I have all this filled up fluid, I can still add solid material but not in connection. So I can add solid here, solid here, solid here, solid here, solid here, solid. But this is not a continuous phase. So whatever stress you put on top will be responded by the continuous phase, which is water. So this whole thing, even though it has lots of solids inside, will behave as if it is a liquid. So once it behaves as a liquid, it will plot as a liquid. It plot as a liquid, right? So this is where the understanding of your geology and geophysics comes to your help in order to understand what is the physics of the rock would be. But before you understand the physics of the rock, you need to understand what a mineral is, how a combination of minerals can be used to tell the strength of the rock. And this is again a live example. What is this? Now heterogeneity and homogeneity. So what I'm saying, heterogeneity and homogeneity, it means the fabric texture is very uniform here, and here you have a lot of works and cracks and all those things. Now look at the behavior. What is this? Shear modulus. Now a lot of engineers use shear modulus in their engineering calculations, right? In landslide assessment, a lot of shear modulus is used. A lot of shear loss is investigated. And what is this? This is log of frequency, means you are at 0 frequency, means you are just static. Frequency 1 means 10 hertz. This is 100 hertz. This is 1000 hertz. This is 10,000 hertz. So what are we doing? We are going from static reservoir to seismic to logging to ultrasonic. So we have all the frequencies, all the tools plotted on these axes, and we have shear modulus in terms of value. And you can see that as we are going from static to ultrasonic or the logging, the values are changing. The values are changing. There is a change in value, this much appreciation in value of the property. Now this is important to understand. Why? Again, depending on the tool you are using, let's say you are using logs or using seismic, you should be aware that how much of a difference or uncertainty in estimation of a property you are faced with. But you will not know that unless you have a forward model for that. So you can have forward model for a facie which is very uniform, or a heterogeneous facie which is uniform also, like uniformly heterogeneous, right? So I just wanted to emphasize this in terms of last example. This would be the last example for the time allotted. On the y-axis, although I have many more, on the y-axis you have elastic moduli normalized to dry state. So I'm putting everything as dry. This is a dry value, right? The red is a shear modulus and the green is the bulk modulus. And shear modulus, bulk modulus, they are commonly used everywhere. NIMB is natural imbibition, means there is no force used, and the F5MB is force used for imbibition. Force, how much force used? Equivalent to the formation pressure. And these are the three samples used. One is homogeneous sample, one is intermediate sample, one is heterogeneous sample. We have three samples plotted for bulk modulus and plotted for shear modulus. And you can see this is the saturation axis. This is saturation. So once we started with the natural imbibition, we did not force anything. We started from 0. It went from 0, 0, 0. So my three samples. So this is the first stage, natural imbibition. So this partly heterogeneous sample acquired this much fluid. The fully heterogeneous sample had this much fluid, and the fully homogeneous sample had this much fluid. So given equal treatment of the fluid, equal treatment of the conditions, your facie is absorbing or your facie is releasing different amounts of fluids. So that's very obvious. Like if you get to measure properties on these facie, they will be very different. So that's why in terms of seismic, if you want to understand the amplitudes coming of these phases, you need to understand the forward models, how much of a difference could be. And in force imbibition, see, force imbibition absorbed like 80%, on the intermediate sample went 90%, and the fully homogeneous sample went up to 98%. Again, difference. So this is how the bypassed oil was assessed, that which phase will have lots of bypass oil left. Not only this, in terms of responsive elastic property, so the fully heterogeneous sample is here. This is the appreciation as compared to the intermediate heterogeneous sample, and this is the appreciation in compared to the fully homogeneous sample. So if this is the kind of difference that you're looking in the amplitude values of the elastic moduli, then these are like serious issues. You need to, in order to understand your reservoirs in terms of formation and the fluid they are in and the pressure situations they are facing, right? The wettability and all those conditions that exist in the reservoir. Well, I think I would like to, because I had 4:30, I don't know whether I can go ahead. This is exactly 4:30, but I had some other examples to share with you, but it's not the time right now, because it's a really vast topic actually. So with that, I will end actually. And this is one of the very recent work that we're doing in digital rock physics. I wanted to share, but anyways, we'll have some other time. And yes, I'm open to questions now in case there are any questions, if the audience would like to interact.
Yes, please. Anyone has any queries for sir? You can either speak out or type in the chat box.
Ranjan.
Yes, sir.
Hello,
so you
Ranjan.
can speak.
Yeah.
Yes, sir.
Yes. Thank you, sir, for covering so many things in a very short period of time, right from petroleum system up to this well logging and all this. Sir, I have a very simple question. That's for my understanding. Can we measure the secondary porosity with the help of Warren logs?
Yeah, if you subtract the density to sonic, you can. If you just
Density
put a difference of sonic to density to sonic, because
okay.
yeah, because density looks at the matrix mostly, and the sonic looks at the caveats in between whatever fractures and works it has to travel through.
Okay. So we have in our Upper Assam basin, some of the geologists have informed me that they have encountered a high resistivity against a clean sand body. But when they drilled a well, they didn't get anything from the reservoir. What may be the reason, sir?
So high resistivity in a thin sand body.
No, the sand is very thick. Resistivity also very high. Yes.
So is the sand very tight?
Thick sand body. Yeah, yes. Maybe it may be tight sand, but it shows a good reservoir. But they didn't find any crude oil or gas from that horizon when drilled a well.
So as you were saying in the beginning that there is a sand body, the resistivity is very high, and the sand is very tight.
Yeah.
Right. So this is nothing but can I go back to the example just to share that?
Yes.
So this is one example I wanted to share. Like, I don't know in terms of high means what. So this is a 3 decade of resistivity plotted here. So this is 1000 ohm meter, and this is 1 ohm meter. Yes. So in terms of decades, you're looking at 100 ohm meter here somewhere, right? So this is like 50 ohm meters. So these are all sands here. I can see these are sands. These are highly resistive, right? So in such a case, now this is in particular is a basin centered accumulation, but in such cases when you know there is a likelihood of getting reserve. So just I'm assuming this scenario that let's say you have a sand, it's highly resistive, it's tight, but then you're also looking at possibility of hydrocarbons.
Yes.
So the idea is, right, this is an assumption I'm saying. So in a basin-centered gas accumulation, you have lots of lenses. So you have lenses, and each lens has some water, some gas. So we know that there is a fluid, but the idea is, I mean, it will not show as distinctly. So this is tight sand. You know, you can see the porosity is very low. It's already, you know, it's like this is 20%. So we are looking at 8% porosity average. This is very low porosity, but this low porosity carries gas. So what is the idea? The idea is to understand which formation has high irreducible saturation of water and which doesn't. So the idea is to calculate for each zone or the prolific zone or the sand zones, where is the irreducible saturation high or where is it's low. So if you are sure that, so in my case, as I'm saying, I'm sure there is a gas, but we don't know where to perforate. So the only indication of perforation is wherever it has very high irreducible saturation. So high irreducible saturation will not let it flow, and the low irreducible saturation let the water flow, and you do not make good economics. So, but the primary idea is you have sand, you have high resistivity. So the sand is already tight. It's cemented sand.
Yes. Yes, sir. Yes. Yes. Thank you, sir, so much. Thank you so much, sir.
Thank you, sir.
Thank you.
Sir, I have a small query. You told about the overweight drilling and the underweight drilling. Which one is more advantageous?
Well, I would say never do it overweight. Let's have a little bit underweight. Let's the formation fluid come in small amount so that you know what fluid is coming, but do not let it too much underweight. So in any case, you have to have it 0.5 pounds per gallon lower than the expected pressure weight. That is the ideal drilling window. So if you go so this is my ideal window. Just 0.5 ppg. I have to keep it less only by 0.5 ppg if I can maintain that. Not only that will give that will tell us what kind of formation fluid that you're getting by not losing too much of it and not by losing getting a lot of kick, you know. But I mean, if you do over, then you are killing the formation. Actually, you're already putting a lot of water into the formation, and it is different to characterize that.
Okay, sir. Thank you, sir. Thank you so much.
Good evening, Ravi sir. Hello.
Any more queries?
Hello.
Yes, please speak on.
Yeah, good evening, Ravi sir. It's Ajay from
Yes,
IIT
please.
Kharagpur. Yeah, I just wanted to know about the anisotropy. When you talk about anisotropy, mostly we talk about the horizontal, vertical versus horizontal permeability. So in my research, I was incorporating the clustering and connectivity to predict the permeability. So how do you see it?
Okay, so that is one aspect of getting anisotropy. If you have permeability, so you are talking about permeability anisotropy.
Yes, permeability anisotropy, but I was looking for the clustering and connectivity anisotropy in fracture reservoirs.
See, a simple way is if you have DSI logs, if you have some DSI logs, you can simply tell if you analyze between your slow and fast shear, then you will easily know that fracture directions, if that is objective. If you know there are fractures and they are causing your flow directions to be vary, then between slow and fast shear you can easily find it out. What was the next question? Follow-up question for you? Follow-up point?
Sir, connectivity. First I look at the clustering and then connectivity, and then it will be used to predict the permeability. So the same in the flow direction is the connectivity direction of high connectivity direction.
Yeah, I mean, in terms of, see, when I so this particular problem can have many we can handle it in many ways, but depending on the particular data that you are looking at. So if I only have to look at the anisotropy, like how much anisotropy a particular formation is. So if I can go out and show some of the data. Can I go out of the mode here? Full mode?
Yes, sir.
Sorry. So oh, I'm sorry. I thought I will use that slide actually.
Okay. Yeah.
So I forgot the name of the gentleman who asked the question.
Ajay Kumar Sahu.
Ajay. Okay. So Ajay, so the way we characterize, I mean, I would like to characterize. So this is a sample here, right? And this sample is investigated in both the directions, in X and Y direction. And in terms of Hounsfield unit, I have this energy distribution. And this is a very homogeneous sample. Now, what I do in terms of creating forward models in such samples, I do a point investigation for the permeability also, like direction dependent investigations. So I will put my small electrodes in perpendicular directions and map it with the energy that we are getting in terms of distribution. So this way I calibrate my each sample and its permeability with energy in terms of scanning. So once I don't know how you are doing in clustering and then trying to predict the anisotropic permeability, but the way we create the calibration file is the way I'm telling you. So if you divide the sample into different sectors, let's say 5 sectors, and this is a particular phase C. So in the 5 sectors, you can see directional dependent change in permeability and the directional dependent change in anisotropy. So if the particular direction here has a link with energy distribution, then I can exactly tell like how the permeability is going to vary with how much of energy. So in the next case, I may not need all the samples from this for this point permeability investigations. But if I have only the scans, I can really prepare a training where I can assign them the permeability value, and wherever those kind of energy distribution is available, the particular permeability can be assigned. So the way we do it in anisotropic formation is this.
Okay, thank you, sir. It was really helpful for me. Thank you.
So any more queries? So if there is none, then we proceed. So on behalf of everyone present in the program, I want to thank Professor Ravi Kumar Saha for his interesting and insightful presentation on a very important topic of petroleum geology geophysics. I believe everyone really enjoyed your presentation. So your presentation helped us to understand about the different things like OPEC countries and also the different types of logs like gamma ray logs, XP logs, resistivity logs, and also about the rock physics modeling method. Thank you so much, sir. So your presentation also showed how important geophysical and geological exploration techniques are for the exploration of petroleum. Once again, from Dibrugarh University, thank you, sir, for accepting our invitation and speaking to us today. Thank you, sir.
Thank you, everyone, actually. Thank you.
Thank you, sir. So we have reached the end of day 1 of this FDP. So on the behalf of everyone of Petroleum Technology Department, I would like to thank all of you for participating and joining in this second section and the first section of this FDP. My sincere thanks also goes to the resource persons for sharing their knowledge and expertise. Please join me tomorrow again at 10:30 a.m. for the third section of this FDP. Thank you so much. Thank you for joining.
Thank you.